So now that we have all these definitions defined and all these words defined, we can actually look at how training affects them, how training lowers some of them, how training raises some of them, how we compare. What would happen if you take an unfit athlete, someone who's never ran a day in their life, versus an Olympic athlete, someone who definitely runs for a living and they're the top of the top, they have a VO2 through the roof. How would the values be different at rest? This is just comparing them at rest. Now, certain things will be different when they start exercising, of course, and certain things are different when they're at rest. But right now, we're just looking at when they're at rest. The next video, we'll look at when they start exercising, how they differ. But at rest, it's always helpful, it's always great to just make a comparison. It's very simple with a comparison. Take an untrained athlete, and what we'll do is we'll pick some numbers. And it's very easy, instead of just memorize, oh, this goes down, this goes up, this goes down, this stays the same. It's much easier to actually have real numbers to go with them. And of course, with all these numbers, you can actually compare yourself. If you're an unfit athlete or an unfit individual, you can just compare your heart rate to a friend who's fit, and you can actually see it happening right there. But an unfit athlete, their heart rate, or if you just take their heart rate, will probably be around 70 beats per minute. Now this is normal. Nothing's wrong with 70 beats per minute. Now, on the second test, when we talk about arrhythmias and everything, we talk more about the SA node and the electrical stimulation and current through the heart. But the heart is essentially it's autorhythmic, which means it beats by itself. It makes its own action potential, so it causes its own contraction. It's not with no nerve impulse, and it does this through the SA node. And we'll just define that because this is kind of important to understand why your heart is at 70 beats per minute, and also why it's low with a trained athlete. The SA node is a little dude inside the heart. He sits in the upper right atrium. And he's just chilling there, and every 60 to 100 beats, or every minute he beats by himself automatically, every 60 to 100 times every single minute. Every single minute for the rest of its life, it's going to be beating 60 to 100 beats per minute. Now, an untrained athlete falls somewhere within this range, which is why I said around 70. It could change, but it's somewhere within the 60 to 100 beats per minute range, and that's perfectly normal. Now, their stroke volume, how much blood they pump out with every beat, will probably be around 75 milliliters. So every single beat out of each of these 70, every single of these beat is pumping 75 milliliters per minute. And its cardiac output, again, you can actually do the multiplication, just times 70 by 75 will be around 5 to 6 liters per minute. If you do this multiplication, it'll be around 5,000 milliliters per minute, but you just divide it by 1,000 to get to liters. So it'll be around 5 to 6 liters per minute. So this will be an untrained athlete's credentials. We'll have all these things. Now a trained athlete will just compare what happens to their heart rate and their stroke volume and their cardiac output. Now a trained athlete, I'm sure you all know, has a much lower heart rate. A trained athlete's heart rate is probably around 45 beats per minute if they're an aerobically trained athlete. And why is it so low? Because you're probably like, oh, hold on. The SA node beats by itself every 60 to 100 beats per minute. How is it possible that the heart is being lower than 60 to 100? It's doing this because the SA node is still doing its thing. It's still beating every 60 to 100 beats per minute. But the heart is also controlled by certain impulses, certain nerves. And a little guy who controls the heart is called the vagus nerve, or vagal, yeah, we'll just call it vagus nerve. The vagus nerve. And this is essentially the parasympathetic activity. This is the rest and digest nervous system that you learn in Anatomy 2 or Anatomy. It slows down the body. It's whenever the body wants to rest and conserve energy, well, not really this guy controls the heart, but the parasympathetic activity, the parasympathetic nervous system starts acting and rest and causes the body to slow down and conserve energy. And it controls the heart through the vagus nerve, which is part of this parasympathetic activity, and it does it through the neurotransmitter acetylcholine, or acetylcholine, whatever you want to call it. So really, all these words are synonymous. Vagus nerve, vagal tone, parasympathetic activity, acetylcholine, same thing. But essentially, a trained athlete will have a lower heart rate at rest. Now, you can guess what happens to their stroke volume. So since they have a lower heart rate, they must have a higher stroke volume. Because remember, they have the same. Remember in the other video, I said a trained and untrained athlete have the same exact cardiac output at rest. So since they have the same exact cardiac output and the heart rate is low, the stroke volume must be higher, and it is. It's around 100 to 110 milliliters. As you can see, that's much higher. So the reason why this vagus nerve is active in a fit athlete is because their heart is actually stronger. The heart is actually stronger, so it doesn't have to beat as many times to pump out the same amount as blood. Now the body is pretty lazy, so it loves to conserve energy. So when its heart is actually strong because it's pumping out more blood, it doesn't have to beat as much. So it realizes that, and it's going to chill down and stop beating as much to conserve energy, which is why you have more vagal tone and whatnot to conserve energy. So your heart beats less, but you still get the same cardiac output. So you're still getting the same amount of blood, you're just beating less, and thus you're using less energy. Now the reason why your stroke volume is between 100 and 110 beats per minute, because you have to know what is causing the stroke volume to increase. We know what's causing heart rate to decrease, it's parasympathetic activity, everything, but what is causing stroke volume to increase? Something has to be causing you to pump out much more blood with every beat. And that is mostly because exercise increases your blood volume. It actually increases the volume of blood that you have in your body. The exact mechanism I can't explain, but essentially you have more, your blood cells multiply and everything with exercise, and you have more blood in your body. More blood in your body means you have more blood to pump out. More blood to pump out means a higher stroke volume. And cardiac output is the same thing. Now, since cardiac output is the same for a trained athlete and an untrained athlete, it's very easy to see what happens with VO2. VO2 equals cardiac output times AV difference. If cardiac output is the same, VO2 must be the same. And the reason is because when you're at rest, it doesn't matter if you're the elite athlete in the world, whatever, or you never ran a day in your life, your body still needs the same amount of oxygen and the same amount of blood. So it's not going to have a higher VO2 or a higher cardiac output. And then mean arterial pressure will be, there will be a slight difference, but it will mostly be the same. And again, looking at the formula, since they're in rest, remember the heart rate's below 100, will be 1/3 diastolic blood pressure minus systolic blood pressure plus diastolic. Now it is true exercise does lower your blood pressure. Everyone knows that, but it doesn't do it to a significant extent. And we're not factoring in that this untrained athlete is hypertensive. They have a high blood pressure. We're saying they mostly have the same blood pressure. So thus mean arterial pressure will roughly be the same. Now rate pressure product, I'm sure everyone can guess what it does. I'll write out the formula so you can have a chance to guess what it does. Heart rate times systolic blood pressure divided by 100. Now how would a trained athlete's rate pressure product differ than an untrained athlete at rest? Now remember, rate pressure product, you can just say is the stress on the heart. When rate pressure, it's the indirect oxygen consumption of the heart, but let's just say it's the stress on the heart because that's an easier term to understand. Now, if it's the stress on the heart gets stressed, the harder it works, right? Obviously, if you work harder, you get stressed. So since the heart's working less hard or less at rest, and the trained athlete, the heart rate's lower, what will happen to the rate pressure product? Now, if you guess that rate pressure product will be lower, you're correct. Because again, you can memorize that, or not memorize, but you can know that it's less stress, or you can just look in the formula, heart rate times systolic blood pressure. You know heart rate is decreasing in a trained athlete. So if heart rate is decreasing by proportions, rate pressure product has to be decreasing. So you can just memorize that, or you can just look in the formula. It's very easy just looking at formulas to tell how everything changes. If one thing's changing, another thing's changing. And now the last one is parasympathetic activity. We already discussed that. In a trained athlete, it'll be lower because they have more it'll be higher in a trained athlete because they have more vagus nerve. Now sympathetic activity that's like epinephrine, norepinephrine. Remember, sympathetic is fight and flight. It excites your body. It gets your body ready to contract more, pump out more blood, everything, get ready to fight and kill someone. So if your parasympathetic activity is decreased, which is telling your body to rest and digest and conserve energy, it doesn't make sense to have your sympathetic also increase. So your sympathetic is actually lower in a trained athlete. This is all trained athletes I'm talking about. Now it's very easy to just take a graph of everything we just said, because we just said a lot of things and a lot of numbers and how they all changed. So just remember this graph. So the graph is we have heart rate, we looked at? We looked at stroke volume. We looked at cardiac output, VO2, mean arterial pressure, rate pressure product, parasympathetic activity, and sympathetic activity. Now this will be for a trained athlete. Now a trained athlete's heart rate will be lower at rest. So this is looking at rest. A trained athlete's heart rate will be lower at rest because of parasympathetic activity. You can just test that by find the top cross-country runner in school, take their heart rate, it'll probably be around 40. And your heart rate will probably be higher than 40. Just because it's perfectly normal, but he has more parasympathetic activity because his heart is in better shape. Their stroke volume will be much greater when they're at rest, because since the heart rate is low, the stroke volume has to be greater. The cardiac output will be the exact same, because remember, everyone needs the same amount of blood regardless when you're at rest. Very important to note, at rest, regardless of how in shape you are. If their cardiac output is staying based on the formula of VO2, just look at the formulas, then VO2 has to stay the same. Mean arterial pressure stays the same, because there's not a significant difference in blood pressure. We're assuming this untrained athlete isn't hypertensive. Rate pressure product is the stress on the heart. That will decrease. A fit athlete will have less stress on the heart at rest. Parasympathetic activity will increase because heart rate is increasing or decreasing. Vice versa, since parasympathetic is increasing, sympathetic must decrease. Fight and flight, rest and digest. Can't have both these elevated. These are antagonists, so if one is elevated, one is decreased. If this is higher, which it is when you start exercising, this decreases. So that's how you compare an untrained athlete to a trained athlete. And you can have some fun. Just find the fittest individual in class and find the most out of shape person in class and take the vitals, and you can actually see how the heart rate differs, or stroke volume. Well, you probably can't tell stroke volume, but you can at least see how the heart rate differs.